Good afternoon, everyone. I think now we are ready to get started. We ended on this particular slide, I think. If memory saved me, has managed to save me right. Where we were looking at covalent crystals. So we looked at the first type of crystals, which we called the ionic crystals. Now we have second type, which is the I think for one of the groups we went past this slide, but for the sake of those that might be joining us from the other group, that is group 2, we can start from the second one. So the second one, we're looking at molecular crystals. So molecular crystals, what we have are individual molecules in the structure which are held by intermolecular forces. So when you look at the individual molecules in this particular type of crystals, and you examine the forces that are holding the structure itself, you are looking at intermolecular forces. So these are strong covalent bonds that exist inside the molecule. That is what you are looking at. But then for the molecules themselves, they are held together in the structure by the forces of attraction that we talked about. So inside the molecule, you have got covalent bonds that are holding the atoms together. Then the molecules are held together in the structure by intermolecular forces. So these are the London dispersion forces. We talked about the dipole-dipole forces of interaction. We talked about hydrogen bonding. So when you compare the covalent bonds which are holding the atoms together in the structure and the intermolecular forces, you see that the intermolecular forces are 10 times to 100 times weaker than the covalent bonds. So this explains the reason that you are going to have these crystals or substances that have got these types of crystals. Some of them have got low melting and boiling points because of the presence of these weak forces in them. Others are very soft. You can actually cut them with a knife. Yet still we have some that are going to portray properties such as volatility. They evaporate easily. When you compare the electroconductivity with the ionic crystals, which we did talk about, you're going to see that these ones do not have ions in them. So because they have got no ions in them and they've got no free electrons in them, they do not conduct electricity. In other words, they are poor conductors of electricity. Okay. Here we have an example, a diagram, a beaker showing water floating, ice floating on water because of those open hexagonal structures that we talked about where there are going to be empty spaces and you've got the volume of ice increasing and its density is reducing. So water floats on, ice floats on water, and this is benzene. Benzene sinks to the bottom of water because it is dense. Although, of course, in benzene, you only get to have London dispersion forces. So the melting point is way, way lower compared to that of water. So its melting point is about 5.5 degrees Celsius. Okay. We have another type of crystal called the metallic crystal. So these crystals have got positive metal ions, okay, which are embedded in this structure in a lattice form, some pattern of some sort. Then you have free electrons, which are referred to as delocalized electrons, which are able to move throughout the structure. So the force of attraction that exists between the positively charged metal ions and the free electrons, that is referred to as metallic bonding. Okay, so metallic bonding is an electrostatic force of attraction that will exist between the positively charged metal ions after they would have lost their outermost shell electrons, which still remain trapped inside the structure itself. Okay, so that force of attraction that exists between those two opposite charged particles, that is what is referred to as metallic bonding. Then amongst metals themselves, when you try to compare their properties, you see that some metals have very high melting points and others have got low melting points. So you might want to try and understand why that is so. So um, if you picked two examples, you looked at sodium, for instance. If you compared the melting point of sodium and tungsten, you will notice that sodium has a, a melting point of, okay, it's got a melting point of 98 degrees Celsius. It is a metal. Compare this with tungsten. Tungsten has a melting point of 3,422 degrees Celsius. Okay, so then you might want to try and find an explanation as to why this one has got a very low melting point, this one a very high melting point, and yet both of them are metals. So this is because of the arrangement of the atoms in the structure. And also, it's got everything to do with a concept that I introduced to you some time uh, back, which is charge density. We referred to that as charge density. Okay, so charge density was referred to as the ratio of the ratio of the charge that is found on a particle in relation to its size. So tungsten has got a very high charge density, and that makes the forces of attraction that exist in its structure to be way stronger, to be way stronger, and as a result, it has a very high melting point. So now, you see the earlier, sorry, just a digression. The earlier plan was that we were supposed to have our class at 11 hours. Then I was told there was going to be biology at 11 hours. And then 12 hours we still could not meet. So now I start to get phone calls from the second years. At this very time when I'm teaching you, there's supposed to be a class for the second years. So if I go mute for a minute, it's because I'm trying to pick a call from their representative. Let me just communicate that I'm in class with you guys. Wisdom. Okay, yeah, sorry about that. I was just trying to communicate with a gentleman. Okay, so we are saying the higher the charge density, the stronger the forces that are going to exist. in the structure um, uh, amongst the particles, and the higher the melting point, such as in this case. Then some other properties that you are going to have associated with the metallic crystals are that these structures will have properties such as, okay, you have malleability, and you have ductility. Ductility. So malleability is the ability of a metal to be, hammered into sheets. So why are metals uh, able to resist breaking when you hammer them into, thin sheets? This is because as you apply force and the layers shift one away from the other, the electrons are able to quickly re-establish the, you know, the what is the forces of attraction that existed before the layer was moved from one location to the other between the positively charged metal ions and themselves. Okay, so in other words, what we're saying is that um, ductility, maybe we can put them together as we explain what happens. So ductility is the ability of a metal to be drawn into very thin wires without breaking. So why is that possible? This is because the layers of, cations, the layers of cations that you have in the structure are able to slide on top of, one another, and the electrons, the sea of electrons that you have will quickly manage to reform the bonds instantly so that the structure does not disintegrate. Okay, as you are spreading the layers, the electrons are able to reestablish the connections, the forces of attraction, and thereby the structure itself remains intact. Okay, another very important property that metals have, which you might be asked, explain the reason that metals are said to be lustrous. Okay, or maybe we give you the noun version of the word. Okay, the luster. So the word luster, it can be used in a different form. We say metals are lustrous. Okay, you're trying to describe their nature. So why are metals lustrous? This is because the electrons that they have in them, these electrons are able to absorb, they're able to absorb photons from light energy when it is directed at them. So when they absorb these photons, then they are going to re-emit them, and thereby that is going to give them, this ability to uh, present themselves as the objects that are able to shine, because they absorb these photons, then they re-emit them. That is the abilities that they have, and we should be able to explain these properties when questions are asked. Explain the reason that metals have got these properties such as malleability, ductility, and luster. Why are metals lustrous? So you explain in the way we have explained it. Why are metals said to be um, ductile or metallic crystals? In this case, we may not refer to them as metals per se. We will be focused. We will focus our questions, or we will phrase our questions in such a way that they are going to refer to the types of crystals that we have talked about. And one such crystal is a metallic crystal. And if questions are asked, I may not ask a question to say metals. I'll simply tell you to say state 2 or 3 properties that metallic crystals have, and explain why they have those properties that you will have talked about. Okay. In terms of their electrical conductivity, they are very good conductors of electricity, and they also manage to conduct heat energy to a very great extent compared to any other types of crystals. This is because they've got 3 electrons that are able to move. In terms of heat conductivity, remember that as the electrons are moving, they would carry some energy, some heat energy with them, and of course the heat energy can still be transmitted from one part of the metal to the other through the simplest means of transmission, which is conduction. So one atom absorbs heat, it passes that heat energy onto the other, and of course, to a certain extent, that is facilitated by the movement of these free electrons that they have. Okay. So here we have a summary of the properties, the types of crystals that we have looked at, and also their properties. So basically, what we're just looking at are the ionic, crystals, the covalent crystals, the molecular crystals, and the metallic crystals, and the units that hold the structures together. Types of forces, the units that we have, and the forces of attraction that are there, and the examples also. So it's just a summary of everything that we have talked about. Okay. The phases. So we have what we refer to as phases. Okay. So uh, so I'm supposed to have. Let me do this. So the let me stop sharing. Then I will reshare. So I don't know. It's just the software which is not able to display some features in the PowerPoint. So it keeps doing this. Sometimes it will pop up, then at another time it just completely disappears. So just bear with me. Let me put up this again. Yeah, so it keeps doing that. And as a result, when you try to display it, it's refusing. Okay, so this is what we were supposed to have gotten on phase changes. I don't know. I'll probably just need to remove some things they are not able to show when the software decides to perform. Okay, so here on this slide we're dealing with the phase changes. So the phase changes, we are looking at processes that involve energy and what we call order changes. So it's the part that is not very clear this side, you've got least order this side, you've got greatest order the other side. Greatest. Got the greatest order, and then on the other side, we've got the least order here. So on the slide itself, when we move from left going to the right, we see that we've got processes that are endothermic in nature. You have melting, you've got, this is vaporization, and you have sublimation. So these processes involve breaking bonds. And if you're going to oh, oh,
Now your phone will switch off the access.
try to see if I can mute this friend of ours. Okay. Seems to be listening in with the entire family. Okay. So we are saying these processes will involve supply of heat energy for you to break the bonds. Recall how we defined endothermic processes as processes that would absorb, heat energy from the surrounding environment. When we reverse the direction, we start to move from the right going to the left this side. We see that we've got processes that are exothermic in nature, such as freezing, you've got condensation, you've got deposition. Okay, so all these processes involve release of some form of heat energy. So why are we looking at these processes? Because we would want to at some point understand how particles of substances behave when they are participating in chemical reactions or systems where you have particles interacting together. Okay, so to try and understand, these properties of these particles in terms of how they are going to uh, behave as they interact with others in a given system, we would like to bring in the concept of what we refer to as entropy. Okay, so entropy is defined as the degree of disorderliness of a system, okay, which is given by that. So how disorderly things in a system are is referred to as, entropy. And the more disordered they are, the higher the entropy or change in entropy. Okay, the higher it is going to be. So for solids, because their particles are fixed, they have got the least entropy compared to the gases whose particles have got, the freedom to move from one location to another. They are free to move through long distances as far as the kinetic theory of matter is concerned. So to understand this better, we go to these two distribution curves that we have, which can be used to explain the behavior of particles in a given system when you are looking at the way they are going to interact with other particles. So we use what we call the Maxwell. So the Maxwell, we've got the Maxwell-Boltzmann. Okay, distribution curve or curves. So these distribution curves can be used to explain the behavior of particles when substances are interacting with, when the particles of different substances are interacting with one another. So you recall that we had told you that according to the kinetic theory of matter, matter is made up of particles that are very small, and these particles are in a constant random motion. It doesn't matter whether the substance that you're dealing with is a solid, liquid, or a gas. The particles are moving, even if it means them moving in those fixed positions where they are going to keep doing that. So if you had two reactants A and B, okay, put together, their particles are supposed to collide, and as they collide, they should do so with the amount of energy that we refer to as sufficient energy, which is also known as the activation energy. Okay, so when you increase the temperature of the particles that are reacting together, they are going to gain heat, and this heat energy that they will have gained is going to give them what is the energy of motion referred to as kinetic energy. Okay, remember these particles before they start to interact with it, they say the particles of A, before they start to interact with the particles of B, they have some forces that are holding them together, which are the intermolecular forces of attraction. Okay, so you need to overcome the strength of these forces for you to allow the particles to acquire the minimum amount of energy, which is equal to the activation energy, for them to interact together and form products. Okay, so When you apply heat energy and you keep increasing the amount of heat energy that you will have applied, what you're trying to do is that the kinetic energy that these particles are going to have, okay, should be greater than the strength of the intermolecular forces of attraction that are holding the particles together. Okay. So then this means that if the particles of A and B have got kinetic energy which is greater than the strength of the intermolecular forces, then it means the particles would have reached the activation energy. They will have acquired the kinetic energy. They will have acquired the activation energy that is needed for them to, manage to interact together and form your products. So if you're looking at a very simple setup where you have molecules that are trying to escape from a surface through a process that we refer to as evaporation. So the higher the kinetic energy, the weaker the intermolecular forces of attraction holding the particles together are going to be, and the easier it becomes for the particles to rise from the surface. So in other words, the rate of evaporation increases with temperature. The rate at which the reaction is going to take place is also going to increase with the temperature. So this is what this is basically about, the Maxwell-Boltzmann distribution curve, which helps to explain the effect of temperature on the behavior of particles of substances as they try to interact with other particles of other substances. Okay. The equilibrium vapor pressure. So this one refers to the amount of energy that is, the process. It's a measure of the dynamic equilibrium which exists between the condensation and the the evaporation. Uh, I taught you chemical. I taught you chemical equilibrium and acid-base equilibrium. In chemical equilibrium, we had talked about the conditions that we needed to meet for us to be able to have establishment of a state of chemical equilibrium. And one such condition that we talked about was that we needed to have a system that could not allow anything going out of the system to begin with, or anything coming out of the system. Otherwise, we're not going to manage to reach a state of chemical equilibrium. So think of a reaction in which you have not allowed anything, you're not allowing anything to get into the system or going out of the system, where you have a very simple, reaction that is fluctuating between, forming water molecules in liquid state and forming water molecules in a gaseous state. As long as you do not allow any particles going in there or going out of there, then you're going to have establishment of a state of chemical equilibrium, at which stage the rate of evaporation is going to be equal to the rate of condensation. Okay. And you cannot keep doing that. You cannot You cannot keep doing that. It's not acceptable where there are a lot of people. You don't do that. You mean you can't keep your microphone, muted the entire time. We will remove you from the group and we will lock it so that you don't join back to the meeting. Stop doing that. You don't understand the seriousness of what is going on, do you? Uh-uh. Okay. So the simple setup that we can use to measure the equilibrium vapor pressure of a substance, especially a liquid, is what we have in this particular slide. The setup is called a manometer. So this is a manometer. Okay. So it consists of a flask. The flask has the liquid whose vapor pressure we want to determine. Then it is set up in such a way that you've got this U tube where you're going to have the level on one side of mercury in this particular U-tube is the same as on the other side. Then this side, you're going to make sure that there are no air molecules, meaning the space is evacuated. So you're going to have to measure the, you know, the vapor pressure of what is in here, comparing it with that of the vacuum on the other side. So the way this works is this: that when you allow the liquid to vaporize, the vapor inside, before the liquid, vaporizes, you're going to have a, a partial pressure, initial partial pressure of 0. So the distance or the difference between the index where the mercury was before the start of the experiment and where it is going to be equivalent to the vapor pressure inside the vessel itself. So as the pressure builds up, then you're going to have the mercury index being pushed downwards this side, then on the other side it increases. So this difference is equivalent to the vapor pressure of your substance, or to be specific, you might want to start with V. So this is the vapor pressure of a substance that is in this particular containing vessel. Then the unit that is used is millimeter mercury. Okay. Although of course you can use other units, such as you can use torrs, okay, you can use bars, you can use pascals. Okay, you can still use atmospheres. So at 1 atmosphere is equivalent to 760 millimeter mercury. So at least this gives you where to start from. Okay, so if you knew the relationship between millimeter mercury then and atmosphere, then you'll be able to find a way to convert from atmospheres to torrs, okay, to torrs, bars, or pascals, depending on what the question is asking you to give your answer in terms of units, uh, uh, what units you're supposed to report your answer in other words. Okay, so we know that uh, we have introduced to you guys a lot of things, and we are still introducing to you more things. Okay, and the equations keep piling up. So when I see, I see from a class where previously we would have this number that we have here is actually sometimes it goes up. I'm not sure whether it's miscommunication or whatever might have happened. So we have a number that is supposed to be for the two groups in one group here. So it means most of those that were supposed to be here are not here. You guys don't want to hear the word, failure, but it's real. And when I teach things like this, and most of you are not here, and well, you might manage somehow, but a lot of you will find it very difficult to answer some of the questions, because when you're not here, when these concepts are being explained, then it becomes a problem. And already your work is piling because you have not written your first test, and which you ran away from, by the way. You ran away from writing your first test. There was just one day in between that was there for you to write your first test. Then you decide to run away. Okay. On Saturday, you're supposed to write your test. On Friday, you pack your bags and you go home. So what would you call that? That was running away, basically. Okay. We can't use any other word to describe what happened that day. It was simply just running away. But your running away was not a solution, because uh, you have more work now. You've got the first test, which you're going to worry about. We're still waiting for you to come and write your first test. The moment you show up, we will give it to you. Then on top of that, we will still give you the second test. Okay, so you see how much your problems have multiplied now. Okay, well, you're trying to remember the things that we taught you, chemical equilibrium, acid-base equilibrium. You are learning also other things, and this as well, and everything else that is going to follow thereafter. So it is a lot of work on your part. If we had dealt with that test, then we're going to be worrying only about the second test, you see? Yeah, but well, you had to do what you had to do, and you had your own reasons for doing what you did. Of course, the conditions were not okay, but one more day surely was not going to be a bad idea. Staying just one more day. You write the test, then the next time that you show up, you just go to your second test. So what you see here is an equation called the Closius-Capron equation. So in this equation, this version that you have here is mostly used for experimental purposes. I'm going to show you how to use it to determine what is known as molar heat of vaporization, which is the energy that is required to vaporize 1 mole of a liquid at its boiling point. Okay. So in this equation, the Ln that you see here, what looks like In, that is small letter L, and that is N, which stands for natural. We've got natural logarithms. Okay, logarithms. So, purposes of easily pronouncing it, we just call it ln. The ln of P is equal to negative change in molar heat of vaporization, the universal gas constant, and the temperature in Kelvin. So temperature is the pressure, that is the equilibrium vapor pressure. Then T is the temperature in Kelvin, and R is the universal gas constant. Then there is C, which is a constant. So this one is determined experimentally. It is. I'm going to explain more on how you can avoid using this. Yeah. So in those days when I was a student myself, we would have questions like, the questions that would come on this. I'll show you how to deal with such type of questions in case a question comes. So what we have here are just two plots, two plots that look different, but they are talking about the same thing, essentially. So you're trying to compare the vapor pressure and the temperature at which these three different substances boil. Diether or ether boils at a temperature of 34.6. Then this one at 100 degrees Celsius, and you've got 37 degrees Celsius. So when we design a question, or in those days, whenever we would have these types of questions, you would have a table. So on this particular table, you would have a table where you are given the vapor pressure, okay? Then you are given the temperature. So you have that. Okay, let me do this. So this one, in whatever unit, okay? So in whatever unit, I was trying to include some unit, but it's okay. So in whatever unit these might be, you have those values like that. Okay. Then you are told, using the values in the table, plot a graph of the ln of P against the inverse of temperature, which is indicated there. Okay. So sometimes you would be in a hurry, or you just do not know what to do. You would quickly rush into getting your graph paper, you start planning and all that, and then you make a plot of the values of P and the values of T. Then you would end up with a curve. Then we tell you, using your plot, find the molar heat of vaporization. So this one is supposed to be found, I'll explain more on this, I'm not yet done. So this is supposed to be found from this particular equation here. We see that the gradient, which is slope is equal to negative change in enthalpy of vaporization divided by the universal gas constant, which is R. So this is the formula that you're going to have to use if we ask you to find the molar heat of vaporization. But where does S come from? So S, I'll write it down here. So S is the slope, which is gradient. So this is found by change in Y divided by change in X. We have seen this before. Okay. So when you use this, you're going to throw that into this equation and you use the value of the universal gas constant for you to be able to find the molar heat of vaporization. But if you plotted those values directly the way they are, then you're going to get a curve and you would have to use the tangent method for you to be able to find the gradient of your curve. And the value that you're going to get, if you throw it into the equation itself, it's going to give you some value that you might think is the correct answer, but it is not because you used the curve. So you have to change the curve into a linear, equation, okay, into a linear plot. So how do you do that? You are going to extend your table now. For those of you that are listening in carefully, you've seen I've talked about a lot of things here. So you are going to extend this table here, okay? Extend the table by creating two more uh, columns here. So on one column, you are going to have the ln, okay? That is the ln of P. Then in the other one, you're going to have the inverse of T. So find the ln of P using your calculator, making sure that your calculator is in the degree mode. And then you put each P value this side and its corresponding ln value should go in there all the way up to the last value. Usually you are given about 10 value, 10, yeah, 10 points, maybe less sometimes, or sometimes even 15 of them, so that you have got a perfect plot of sorts. Then you're going to find the inverse of the t values this side. When you've got those two, those are the ones that you're going to use to plot your graph. So you have a graph like this one, where I've got a straight line. Then from this particular graph here, do not make a mistake of using any of the points that you will have been given originally, which you converted to those values that are this side, to find your gradient. We would know, because we're going to look at the table and we would look at the values that you have used in your gradient formula this side here. And if you use those, then there's nothing that you'll have done, because the idea behind you calculating the gradient of a plot is to try and see how perfectly you were able to locate the points on your graph. Okay, so the idea that the strategy to use, which I'm going to you're lucky, I've been guiding you on a lot of things, you guys, okay, on a lot of things. It's most of which in our time we learned it the hard way. We had to find out on a lot of things just on our own. And you guys, luckily, you actually even have notes. Good God. Hmm. There were no notes in those days. You had to make your own notes. Okay. You had to go to the library and then you got this book and you read through this chapter on your own and you came up with the notes on your own. We were not given notes. I don't know who's trying to babysit you guys. Yeah. Okay. So we continue. Okay. So then when you get, so the strategy, like I was saying, is to get two independent points, whose coordinates are not in the table. So pick two independent points. So you're going to pick one point there, you call it 1, then you find the x coordinate, the y coordinate, that is x1, y1. Okay, so in this slope here, you have, this is going to be equal to, So from here, you have y1 minus y2 divided by x1 minus x2. You're mathematicians. So even if you did it the other way around, you say y2 minus y1, x2 minus x1, it doesn't really change anything. You'll still be able to find the same answer. So allocate those 2 points, point 1 with its coordinates x1 and y1, point 2 with its coordinates x2 and y2. Then use those coordinates to find the slope here, the value. Then the value that you're going to find, you're going to throw it in this equation here, and you get the universal gas constant value. Then you compute and you are going to find the molar heat of vaporization. Quite a lot of work, don't you think? It is. So if you found a question like this one in your quiz, it would probably be just the only question that is going to be there. If you found this question in your test, it would require not less than 10 minutes for you to be able to answer it. If you are very fast, then 10 minutes. If you are fast enough, 15 minutes. If you are slow, it would take you an entire 20 to 25 minutes, and you cannot afford to spend 25 minutes on a single question. Okay. So, uh, don't forget what I have guided you on how to deal with these types of questions. I'm not saying when you come to write the test, you find a question exactly like the one that I am from talking about here. No, it might just look similar to what we have done. Yes, there is a question. I told you last time, when you have a question, do not raise your hand. I may not really be able to see you in good time. So ask your question, yes. Just unmute, then you call out to me. Yes.
Oh, thank you very much, sir. I'm going to ask him if you can just
Yes,
do
please.
a quick summary of what you have talked about. I'm a bit behind.
Okay, I've talked about a lot of things. Yes. Okay. All right. Noted. So on this slide, that looks like it's got a lot of things that I have drawn here. I'm not going to erase, because if I erase, it means I'm going to have to start to draw things again. So I will go through what I have said quickly. On this Closures-Clapeyron equation, there is this equation which I would like to ask you to see underneath the writings, because I don't want to remove them. You've got the ln of P, then the molar heat of vaporization, minus, there's a minus sign here, then RT underneath, then there's plus C. The C is a constant which is determined experimentally, that is. And if you are going to use this formula, then we'll give you the value of C so that you plug it into your equation, then you do the computations that need doing. But I did mention that this equation usually is for purposes of experimentation whenever you're going to have to determine the molar heat of vaporization. Okay, so when you carry out your experiment and you end up with a set of values, you're going to have a column of values where you've got the what is the vapor pressure values for your substance. Then you're going to have the temperatures that will correspond to the different vapor pressures that you have. Okay. Then we are going to ask you, using the table of values that you have been given, plot a graph of, let me write this here, a graph of ln, okay? I hope you're able to see up there. Let me move this to the side. So a graph of ln against the inverse of temperature. This is the plot that we're going to ask for. So if you do not know what to do, or you are in a hurry, or simply hoping that somehow your answer is going to end up being the correct answer that you're going to get at the end of the day, then you're going to rush into getting those values and the values of temperature, and you plot them. Then you end up with a curve. Then when you realize you've ended up with a curve, you might be forced to use the tangent method for you to find the gradient, because the question is going to ask you, using your plot, Okay, using your plot, calculate the molar heat of vaporization. So how are you going to find this molar heat of vaporization? You use this formula here. Okay, I'm hoping that through these writings, you should be able to follow clearly where I'm pointing. So slope is equal to minus change in, you know, enthalpy of vaporization or molar heat of vaporization, which is given by that, divided by R. So in this equation, what we are asking you to determine is this, the molar heat of vaporization. So how are you going to manage to find this? You will need to have the slope and you need to have the value of R, which is a constant and it is already there. So you can simply just get it from there. So the only issue is on how to come up with this. So you find the tangent and you find your slope, then you put it in this equation. The answer is wrong. Why? Because the question had asked you to plot the lean versus the inverse of temperature. So what do you do to your table quickly? You don't need to assist to reproduce the table. And if it is in the question paper and you're not going to hand in the question paper, just extend the table there. And then if the table is in the same question paper that you're supposed to hand in, there's nothing wrong with that. Just get your ruler, or even if you don't use one, it's not necessary. Just extend the table by 2 more columns and the equivalent number of rows. Then compute the lean of the partial pressure using your calculator in degrees. Then you put the values there. Then find the inverse of all the temperature values that you have. Then you put them there. When you plot a graph of lean on the y-axis and the inverse of temperature on the x-axis, you're going to end up with a straight line. So then this line that you're going to end up with is now what you are going to have to use to find the gradient whose value you're going to throw into this equation for you to be able to find the molar heat of vaporization. Then the strategy that I said you're going to have to use, do not use the values that are already existent in your table. If you pick two values that are already on your table and you say four points, that is x comma y from the table, then you find the gradient. There is nothing that you will have done. Okay, the idea behind finding a gradient or slope is to try and see how accurate you were in locating your points on your plot or putting the points correctly on your plot. So you pick two independent points on the line that you'll have come up with, which is the graph. So two independent points, you take the x coordinate and the y coordinate, another point, the x coordinate and the y coordinate. So you're going to have x comma y, that is x1, y1, x2, y2. Then that is what you're going to throw into this expression which is here, because slope is equal to change in y, change in x, which is equal to y1 minus y2 divided by x1 minus x2. Then when you find that value, you bring it here. Okay, then you put the value for the universal gas constant and you compute for the molar heat of vaporization. I hope that helped you to understand everything that I talked about at first.
Yeah, yes, sir. Thank you very much.
Someone says I should do an example. What I was explaining was an example there. Okay. But of course, I will give you a slightly different example in the next remaining 5 minutes. Okay, so that equation that you saw, there, which is this one, it can be simplified into this that I'm going to show you here. So to avoid having to deal with the issue of the constant C there, which I'm begging that everyone should be able to struggle and see through the writings, because I didn't want to remove the writings from there. Okay, so for you to avoid dealing with the issue of the constant C, you're going to pick, as you design your experiment, make sure that you design it in such a way that you measure the temperature at two different, intervals of time as you are doing your experiment. So at that interval of time, you would know the time, you would know the partial pressure, the initial partial pressure, which is the P1 there, and the initial temperature. Then at a later stage, after some time would have passed, whether 30 minutes, 20 minutes, 10 minutes, or an hour or two, you're going to measure the temperature and you measure the new partial pressure. So when you've got those two sets of values, then it becomes easier for you to avoid having to do with the constant, such that you can just plug in the initial partial pressure, the initial temperature, the final partial pressure, and the final temperature into this version of the equation and the value for the universal gas constant. Then you'll be able to compute the molar heat of vaporization, which makes it easier. And if the question does not come in that form where we would have to give you a table, it might come into a slightly different form that you're going to see. Okay, so I'm not saying, well, I'm bringing a question with, no. I'm just trying to show you how questions may be designed and how you would have to deal with them. Okay, so a slightly different version of the same formula is this one, but it doesn't really change anything. So you can either stick to this one or you stick to the other one. This is just the rearranged form of this equation. Okay, so I'm seeing we just have a few minutes remaining. I would have loved us, I would have loved it if we had more time, but I'll rush through everything. A diethyl ether is a volatile, highly flammable organic liquid that is used mainly as a solvent. The vapor pressure is directly of diethyl ether is 401 millimeter mercury at 18 degrees Celsius. When the time is 14 hours, I will not end the class until I finish explaining, how to deal with this question. Then that's when I'm going to deal with the second years who are waiting for me. So just hang on. So calculate its vapor pressure at 32 degrees Celsius, given that the standard molar heat of vaporization for diethyl ether is 26.5 kilojoules per mole. Okay, so I present to you two yet again rearranged equations of that equation that we saw in the previous slide there. So you would do well to stick to only one of these versions that I am showing you here. In the first version, in one of these two, they both look like they are the same, yet they're different. In the first one, there is a minus sign, which is not very visible. I'm going to put it there. So that is the part where there's supposed to be a minus sign in this equation. So this one takes a minus sign when you start with the second temperature. That is the inverse of final temperature minus the inverse of initial temperature. Or in the other one, where you do not put a minus sign, you make this part to be positive by starting with the inverse of the initial temperature minus the inverse of the final temperature. You are already in trouble, you guys. You've got so many things that you need to remember and having to deal with. So if I were you, I would say, well, I don't want to have anything to do with anything else except just this equation is the one that I'm going to master, and it ends there. Okay, and of course, the other one, which you should not forget, is the original equation, which would help you to deal with this issue that I talked about. Okay, this part, do not forget this one, because you may need this version whenever you're dealing with the plots. So this one, it's a must. You have to master it. Okay, which you can still extract from the original equation somehow. Okay, so once we circle that part, then we're going to say, well, then because I don't want to have anything to do with you will bear with me. My okay, it keeps doing this, so it's not moving anymore. Let me just restart the PowerPoint, then I will reshare. Okay, I'm still here. Don't worry. Let me just see. It keeps doing this. It seems to have. Okay, come on. Okay, then I'll reshare. Don't worry. Let me just close the app. Open it. Open it. Then we start again. I have to show you how to deal with this. Let me open it again. Okay, sure, we are back. Okay, so we are good to go now. Okay, yeah, so saying we don't want to have anything to do with anything else, we circle this one, and this is the one that we're going to focus on. So from the information given, the initial partial pressure is 401 millimeter mercury. The second partial pressure is what we're going to have to find. The temperatures given should be converted into kelvins. So we add 273.5 to each of these, and we get 291.15 as the initial temperature, and the final temperature as 305.15 kelvins. The value of R is 8.314 joules per mole per Kelvin. Okay, then you notice that in the question, this one is given in kilojoules. The unit for the value of R, what is the numerical value for R, whose unit is given in joules per mole per Kelvin, should be uniform with the units that we should have there. So how do we create that uniformity? We change this one into joules also from kilojoules, and it gives us 26,500 joules per mole. Okay, then when we plug in the values that we have into this version that we have chosen, we are going to get that. Okay. So the initial partial pressure goes there, the value of R goes there, the molar heat, or the standard molar heat of vaporization goes there, then you've got the initial temperature and the final temperature. When you compute the numbers on the right side, you end up with that. Then the entire expression that we have here, this, if you are able to remember, this is the logarithmic form of part of the expression that we, what is what we're trying to compute or deal with. I taught you chemical equilibrium, so we are familiar with how to deal with natural logarithms. So you change to base E, which is the Euler's number. You have seen this one before, the Euler's number. The Euler's number, and I guided you last time that to get the exact value for Euler's number, you have to use the alpha function on your calculator. So go to alpha function on your calculator, then you're going to hit the lean key. Then after that, you will have this is going to show up, rather it's going to pop up, and it should be bold. Okay, the E should be bold. That should appear, not the other type. When the E that is bold appears, I seem to keep putting the bar on top as though it were an electron. Yeah, so when this pops up, it means you'll have gotten the Euler's number. Okay, so then you raise the Euler's number to that number which is there, and you do the computations. You see that you're getting 60, that is 662.6 millimeter mercury. If there are no questions, then I will surely beg to disappear. With your permission, I surely can disappear right now. I attend to the second years who have been very patient. They have been waiting for me patiently. Okay, thank you so much, you guys. I'll see you another time. Thank you.